When light passes through a moving window, it is dragged by that window, although the effect is usually very small, as the amount of dragging is inversely proportional to the velocity of the light through the window, and in most cases the light passes through the window too quickly to be dragged very far. However, when light passes through a spinning slow light material, in which light has propagation velocities significantly slower than the speed of light in a vacuum, the material can rotate the light through an angle large enough to be seen by the naked eye. This is an effect called rotary photon drag, which we use to examine the mechanisms behind slow light. We look at the rotation of a laser beam containing both bright and dark regions to decide between two possible causes of slow light. If, as in Model A, slow light is caused by a simple mechanism of optical bleaching, where the peak of the beam is shifted through differing absorption of the front and tail ends of a pulse, the intensity null could become brighter through fluorescence, but the intensity null would never be shifted. If, however, as in Model B, slow light arises from a more complex mechanism, where the narrow absorption feature gives rise to high dispersion and a correspondingly low group velocity, a region of zero intensity could be shifted to a region that had previously been bright. Our objective is to determine which of these two models is the cause of slow light. We examine the rotation of an elliptical laser beam which is focused down onto the front face of a standard laser ruby crystal. A motor spins the ruby and the light is imaged from the back face of the ruby onto a camera. By observing a rotation of both the bright and dark regions of the beam, we've been able to determine that Model B is correct. The slow light mechanism is more complex than the simple optical bleaching, and rather it depends on the narrow absorption feature giving rise to high dispersion and a correspondingly low group velocity. This research expands our understanding of slow light and paves the way for applications dependent on the preservation of complex patterns in slow light material, such as optical storage, optical memory, and the manipulation of orbital angular momentum carrying beams.